Alright, so in this video I'm gonna be explaining another important article, but this time one of the fundamental problems of graph neural network is feature overcorrelation, and this idea is discussed in KDD Conference 2022 with the title Feature Overcorrelation in Deep Graph Neural Networks. So recent years have witnessed remarkable success of GNN. Despite the success, over-smoothing has been identified as one of the key issues which limit the performance of deep GNNs. It indicates that the learned node representations are highly indistinguishable due to stacked aggregators. So very near neighbors, their features are very close to each other. But in this paper, they propose a new perspective, look at the performance degradation of deep graph neural networks. For example, feature overcorrelation. Of course, overcorrelation and over-smoothing are two different things, but they are related to each other. Another thing is overfitting. Another thing is over squashing, for example. Over squashing, for example, is even harder than over smoothing. It is less overlooked than over smoothing. So there are fundamental problems in graph neural networks that in this playlist we will talk about it. We will be talking about, for example, positional encoder in one of the videos, many videos, positional encoding. And so this paper only focuses on overcorrelation. This overcorrelation here. So to reduce the feature correlation, they propose this model decal. So these are their contributions. So also they tackle over smoothing. So in any graph neural networks, the Lth layer is built upon the L-1th layer. And there are two important things, the aggregation and update. For example, here we call propagation and transform. And we can calculate the discrete label probability distribution of node V sub I. Of course, a graph convolutional network can be solved as simple as this one. So these are the basics, and the important thing in this paper is this Pearson correlation coefficient between two vectors. So they proposed a metric core to measure the correlation among all learned dimension pairs in the representation. And they used the metric SMV, which is proposed in this reference, uses normalized node representation. And D is just you normalized Euclidean distance. So the smaller this SMV, the smoother the node representations are. So we investigate overcorrelation and over-smoothing issues in three representative GNN models: GCN, GAT, ChebyNet. So propagation can lead to higher correlation. For example, in this proposition, they showed that given an extreme over-smooth matrix where each row is proportional to each other, we have this correlation equal to 1. Classic math. Then they showed that given an extreme overcorrelated representation, the rows of X are not necessarily proportional to each other. So transformation can lead to high correlation. So there are potential problems with overcorrelation, that the learned dimensions are redundant and of less efficiency. You see the correlation and smoothness of learned representations for 3 GNNs together with their test accuracy. The larger core is the more correlated the dimensions are, while the smaller SMV is the smoother the representations are. And the core SMV values on Cora, when the number of propagation and transformation increases, they also increase. So, historically, these are the approaches for over-smoothing, which is a related thing. So here they propose for a framework of D-core. So the heart of this is that we can write this equation 8 as a matrix form. And this is the Frobenius norm. So this gradient X transpose, this gradient is calculated as this. So the gradient calculation has this order of complexity, which is not scalable when the graph size is extremely large. So to deal with this issue, instead of using all nodes to calculate the covariance, we propose apply the Monte Carlo sampling to just sample square nodes with root square node n nodes with equal probability to estimate the covariance. Then the complexity of calculated the gradient reduces to just order of nd squared. So amazing reduction by just sampling. You don't need to use all of the nodes, and n of them is enough. N squared, it's a lot of complexity. And this sampling strategy injects randomness in the model training process and thus can help achieve better generalization. So minimizing this loss, this equation 9, is analogous to minimizing the following decorrelation loss, where we normalize the two terms by dividing the Frobenius norms. X can be the output representation matrix for the current GNN layer. So the final decorrelation loss for the explicit representation is this, because we have k number of layers. And of course, mutual information, that given two random variables A and B, we formulate mutual information like this, like the entropy and the conditional entropy. But it is hard, so we find a lower bound, just like any machine learning problem. Find a lower bound and we focus on that instead. So hence, to maximize mutual information between kth layer hidden representation and input feature, so we minimize the following objective. Okay, so then we sample a set of these h sub I, x sub I from the joint distribution to estimate equation 14. Okay, nice. Then we can apply the above loss function for each layer for deep GNNs. We only apply L sub m of every T layers to accelerate training processes. So this is another trick to accelerate the learning process. So we finally summarize the overall loss, which is a combination of all these two. And you can play with these alpha and beta hyperparameters to see which one is better. And the results on Cora dataset shows that a different node accuracy, node classification accuracy on different layers. For example, if you have 30 layers, the accuracy here is even worse than when you have only 2 layers, because the over smoothing and over correlation have been worsened. So it's interesting that it has a very bad effect on node classification accuracy. So if they compare their methods, DCore is their method, they just use it with different configuration, deep GCN, and they notice that when the number of layers grows from 15 to 30 on the SMV, and the SMV of that, they have three performance measures: accuracy, core, and SMV that we define in this paper. So the SMV is when you go to, for example, another one, when you go the correlation, when you go to 30 layer, is slightly reduced, not as bad as previous slide that I showed you. So this shows the effect of decorrelation. For example, the accuracy 76 is almost the same when your number of layers is increased. So almost the same. Let's check another configuration. So this one, when number of layers increases almost double, then it is slightly decreased. And then for test accuracy and the correlation, you will see different, when the number of layers increases, the correlation value increases. And the test accuracy, of course, always decreases when the number of layers increases, unfortunately. So we just understood that GNN still has many problems, and we haven't done anything to improve these problems. Maybe in future, next generation of GNNs have lots of things to do with hierarchical pooling.